Why do all living things ultimately walk toward death? This is a question we all know, but cannot answer. It's not just life. Even our Earth and the entire universe are constantly moving from birth toward death. This is the fundamental law of the universe. No one can change it. Ever since we began lamenting how brief life is, almost everyone has been asking what the ultimate fate of the universe really is. After endless time has passed, will life still exist? These questions cannot be answered in just a few words. Today, I will start from humanity's first understanding of the universe, traveling through endless galaxies and time, all the way to the universe's final ending. After watching this brief 1-hour video, perhaps you will truly understand what the ultimate fate of the universe really is. We all know the entire universe is not static. It never has been. But for most of human history, we truly believed the universe was static. Looking up at the night sky, the stars seemed motionless. Night after night, year after year, the constellations remained constant. The moon glided smoothly. Planets would drift slightly off course, but always returned. In ancient eyes, all of this was eternal, static, like a great cosmic painting, hanging above the world. Therefore, based on this stillness, we built our understanding of the universe. We believed Earth must be the center, solid and unmoving. Everything else, the sun, stars, heavens, must revolve around us. A perfect celestial dance, driven by something divine yet endlessly repeating. For centuries, this view persisted, not because people lacked imagination, but because it worked. It matched what the eyes saw. It made the seasons meaningful. It explained the alignment of days and nights. It gave us comfort, a stable world beneath our feet, and an orderly sky around us. Then, the illusion shattered. First, Copernicus dared to suggest Earth might not be the center at all. Then Galileo pointed his telescope at the sky and saw moons orbiting Jupiter, proving not everything revolved around us. Next came Kepler, who studied planetary orbits and found planets didn't move in perfect circles, but in ellipses, guided by invisible forces. Following precise mathematical laws, gradually, the silence disappeared. Today we know the truth is far stranger than anyone imagined. Space is not silent and fixed. It's everywhere, constantly moving, not just planets and stars, but galaxies, clusters and superclusters. Even the structure of space itself is moving, stretching in all directions. Yet we still feel motionless. The ground doesn't shake. Starlight doesn't streak past us. The universe feels calm. But this calm is merely a trick of scale, a mirage. Because the truth is, even now, at this very moment, we are spinning on a planet, orbiting a star, racing through a galaxy, while being pulled by forces we can't even see. The vision of a static universe is gone forever. We have entered a story of hidden motion. We're finally beginning to understand what this movement means. For thousands of years, the prevailing view of the universe placed Earth at the absolute center. After all, this is what people knew. During the day, they saw clouds drifting overhead, the sun shining brightly above. At night, they saw the moon and stars, spread out like a vast cosmic canvas. Every celestial body seemed to be moving, while they believed themselves at the center of it all. From Chinese astronomy to Mayan cosmology, this view was found everywhere in the ancient world. But in the Greek world, this idea not only became accepted mythology, but was built into a technical cosmic model. The person who did this was Claudius Ptolemy, around the 2nd century AD. Ptolemy lived in Alexandria during the height of Roman Egypt. He was a scholar, a mathematician, and most importantly, an astronomer. He wanted to understand the sky, not just philosophically, but numerically. He inherited the rich traditions of Babylonian star tables, Egyptian astronomy, and Greek geometry. But what he did with this knowledge was extraordinary. He compiled, organized, and refined it into a systematic cosmic model, and wrote a massive work called the Almagest. This work was profoundly influential, becoming the authoritative guide to the universe for over 1,000 years. In Ptolemy's model, Earth sat at the center of the universe, motionless, with everything else revolving around it. In concentric spheres, the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and finally the sphere of fixed stars. Beyond that, humanity knew nothing. The entire universe was a set of giant nested spheres, perfectly ordered, with Earth as the center of all celestial motion. Each celestial body was embedded in a transparent crystal sphere, rotating smoothly around us. The stars were fixed to the outermost shell, rotating once each day, creating day and night. This wasn't just random guesswork. Ptolemy used observations to make his model mathematically functional. He believed celestial bodies must move in perfect circles, because the circle was the most perfect shape in Greek philosophy. But this created a problem. When people tracked planets over time, especially Mars, Jupiter, and Saturn, they noticed strange behavior. Sometimes planets would slow down, stop, and even move backward across the sky before resuming their forward path. If all planets simply moved in circles around Earth, this retrograde motion made no sense. To solve this problem, Ptolemy introduced epicycles, small circular paths each planet traveled, while the entire smaller circle moved along a larger circle called a deferent around Earth. So, a planet didn't just orbit Earth, it orbited a point that itself orbited around Earth. This circular motion could recreate the backward steps seen in the sky. But even this wasn't enough. The mathematical calculations didn't perfectly match what astronomers observed, so Ptolemy introduced another adjustment: the eccentric point, an imaginary point slightly offset from Earth's center. He claimed, if planetary motion was measured from this eccentric point, the movement appeared uniform, not from the actual center, but from this offset position. This model was refined over centuries, polished and preserved. It shaped calendars, timekeeping, astrology, and religious worldviews. It served empires and guided scholars. It explained celestial phenomena for over 1,000 years, but no matter how complex, it couldn't hide the truth forever. Observers began asking sharp questions. Some began searching for simpler explanations. One name stands out, a name that still echoes with revolution today. It all began in 1543, with the publication of a book that shook astronomy's foundations. The book was called On the Revolutions of the Heavenly Spheres. The author wasn't some famous scientist or philosopher. He was a priest. His name was Nicolaus Copernicus. This might sound strange today, but it made perfect sense then. The church was the center of intellectual life in Europe. If you wanted to study mathematics, astronomy, or philosophy, the church was where you learned. Monasteries and cathedral schools were the libraries and laboratories of their time. Copernicus was born in what is now Poland, studied law and medicine, dabbled in economics, and was fluent in Greek and Latin. But his true passion was the sky. For years, he had been quietly collecting observations, making calculations, and writing down ideas forming in his mind that went against everything he'd been taught. His ideas challenged the entire system people believed in. So he had essentially kept his views private. For decades, he hesitated because he knew the risks. Not just scientific criticism, but fierce religious and political opposition. Near the end of his life, he finally, reluctantly, published these ideas. In his book, he outlined a model of the universe where the sun, not Earth, sat at the center. He said Earth was just another planet, like Mars and Jupiter, orbiting the sun once every year. But he didn't stop there. Based on his observations, Copernicus proposed 3 different motions for Earth. First, Earth rotates on its axis once every 24 hours. It's this daily rotation that makes the stars appear to rise and set in the sky. Second, Earth orbits the sun once each year. This revolution around the sun explained the changing positions of planets and seasons. Third, as Earth travels in its orbit, it wobbles slightly, tracing out a small circle. We now connect this motion to Earth's axial tilt and precession phenomena. These ideas weren't just guesses. Copernicus spent decades developing complex geometric models and astronomical tables. He used trigonometry to calculate the relative distances of planets from the sun. He ordered them based on how fast they moved across the sky. The closer a planet was to the sun, the faster its orbital speed. This matched perfectly with what he observed. But despite Copernicus's model being conceptually sound, it didn't improve accuracy. This was because he still assumed planets moved, like Ptolemy, in perfect circles. This made his predictive results about as good as the old system, and in some cases, even worse. Then came the telescope. It wasn't invented by a scientist. Actually, it started as a Dutch novelty. Just a few lenses cobbled together by eyeglass makers. But when news of this strange device reached Italy, one man saw more than just a novelty. Galileo. He didn't invent the telescope, but he turned it into a real scientific instrument. In 1610, Galileo aimed it at the sky. What he saw would shake the foundations of the old order. First, he pointed it at the moon. It wasn't the perfect, smooth, divine sphere people had believed. It had craters, mountains, and shadows. It looked a lot like Earth. Then he turned to Jupiter. He spotted for tiny points of light, circling around the planet. Night after night, he tracked them. They shifted positions, but always stayed close to Jupiter. They were moons, orbiting a planet other than Earth. That was huge, because the geocentric model claimed everything had to revolve around Earth. But Jupiter, with its own system of orbits, stole the spotlight. Next, He observed Venus. Like the moon, Venus went through phases. Sometimes it was full. Sometimes just a thin crescent. That only made sense if Venus was orbiting the Sun, not the Earth. If it orbited Earth, you'd only ever see one phase. But if it went around the Sun, and we were moving too, geometry suddenly made sense. That little bright dot proved Copernicus was right. But Galileo wasn't the one to crack the final mathematical puzzle. That task fell to someone else. A man who at first didn't even believe Copernicus. Johannes Kepler, a German mathematician and astronomer. Deeply religious, insatiably curious, and obsessed with precision. When he became the assistant to the last great naked-eye astronomer, Tycho Brahe, it led to a major breakthrough. Brahe was a Danish nobleman who spent decades collecting the most accurate measurements of planetary motion ever recorded, all without a telescope. On his island observatory, he built giant instruments and mapped the planets' positions with incredible precision. Brahe didn't accept Copernicus' model. He had his own hybrid theory. Planets orbiting the Sun, and the Sun orbiting the Earth. He tried to bridge the gap. But when he died in 1601, he left all his data to Kepler. Kepler dove right in. He spent years trying to make the Copernican system fit Brahe's observations, especially for Mars. Mars was tricky. It didn't move in a simple circle. It sped up, slowed down, looped in the sky. It just wouldn't behave. For years, Kepler tried to force the data into a circular orbit. Everyone thought that way. Circles were divine. The perfect heavens had to move in perfect loops. But Mars didn't care about philosophy. So, Kepler finally stopped forcing the math. He let the data speak. And what it said changed everything. Kepler discovered that planets don't move in perfect circles at all. They travel in ellipses. That became his first law. All planets orbit the Sun in elliptical paths, with the Sun at one focus of the ellipse. Meaning, planetary orbits aren't perfect circles. They're stretched out. Kepler also noticed something else. Planets don't travel at a constant speed. When they're closer to the Sun ... they sweep through space faster. When they're closer to the Sun, and slower when they're farther away. This is his second law. The line connecting a planet to the Sun sweeps out equal areas in equal intervals of time. In other words, as a planet moves along its elliptical path, whether it's near the Sun or far away, the area it sweeps out in a month is always the same. This explains the odd speed changes of planets, especially Mars. Then comes the third law. It tied the whole system together. Also known as the law of periods, Kepler discovered that the square of a planet's orbital period is proportional to the cube of its semi-major axis. Put simply, the farther a planet is from the Sun, the longer it takes to complete one orbit. And this relationship can be predicted. Galileo's telescope and Kepler's equations together produced something extraordinary. One gave people a new view of the universe. The other gave them the math to prove it. Copernicus sparked the revolution. Galileo fanned its flames. And Kepler built the framework to keep it standing. Once the door was open, it didn't take long for someone to walk through and push things forward. The next generation tackled the next big question. Why do planets move? What force keeps them in orbit, stopping them from flying off into space or crashing into the sun? This is where the famous falling apple comes in. Newton gave this invisible force a name. Gravity, he realized. The same force that pulls an apple to the ground also keeps the moon in its orbit, drives Earth around the sun, and governs the motion of the planets. He expressed it as the law of universal gravitation. According to him, every object with mass pulls on every other object with mass. The greater the mass, the stronger the pull. The farther apart they are, the weaker the pull. With Newton's law of gravity, we can figure out that Earth orbits the sun at about 1,070 kilometers per hour, nearly 30 kilometers per second. Mercury moves even faster, around 47 kilometers per second, because it's closer to the sun and feels a stronger gravitational pull. Mars, being farther away, moves more slowly. It all fits perfectly. The closer a planet is to the sun, the faster it has to move to stay in orbit. Newton's math proved it. He linked the motion of the heavens to the motion on Earth. For the first time in history, we had a set of laws that applied to everything. And just like that, the great mystery of planetary motion, why they move, how they move, and how fast they move, was no longer a mystery. It's gravity. But there was something else. Something no one saw coming. Because as scientists used better tools and sharper math to map the skies, they noticed another kind of motion, something bigger and deeper. We once thought the sun was still, but it's not. It's moving too. But where? After the Copernican revolution, the sun replaced Earth as the center of it all. The universe no longer revolved around us. Right now, the Earth is moving, spinning on its axis, and orbiting around the sun. That idea once felt absolutely revolutionary. But once the mindset shifted, a new model, the heliocentric model, began to settle in. The sun, once just another object in the sky, an ordinary point of light, now became our fixed point of reference. The anchor of the cosmos, solid and unmoving. For 700 years, this idea endured. But that was about to change. Not because of a physicist, nor a philosopher, but a musician. William Herschel, born in Germany, later moved to England as a composer. But he was obsessed with telescopes. In his spare time, he built them, grinding mirrors by hand and designing optics far better than almost anything of his era. When he aimed his telescope at the night sky, he wasn't just looking, he was calculating. Herschel became fascinated by structure. If the sky is full of stars, are they scattered randomly or in patterns? He decided to find out the hard way. Through sheer counting, he and his sister Carolyn launched a massive survey. He'd count the stars in narrow strips of sky, just a few degrees wide, recording in every direction how many stars could be seen. Over time, this meticulous work painted a picture. He noticed something odd. Some directions had far more stars than others, and the densest band lined up perfectly with the dim, hazy streak we call the Milky Way. So he mapped the sky based on star counts. From that, he built what he believed was the shape of the universe. It looked like a flattened, stretched disk. A giant grindstone, with the sun sitting roughly in the middle. Today we know he got the size wrong. He didn't account for interstellar dust, which blocks the light from many distant stars. But for the late 18th century, it was groundbreaking. He had realized the stars weren't infinite. They were part of a structured system, and we were inside it. He called it the Milky Way. But Herschel didn't know it was a galaxy in the modern sense. He thought this system was the entire universe. He didn't realize those fuzzy patches of light, the so-called nebulae, were actually unimaginably distant galaxies. Still, what he saw was nothing short of revolutionary. He showed that we weren't the center of everything. Not even close. And that flat shape had meaning. It hinted at the direction of the system's motion. If the Milky Way had a shape, then we had a location. And if we had a location, maybe we were moving too. From then on, people began asking a deeper question. Where exactly are we? And how do you know what's moving? And what's not? Because if everything is moving, how can you tell when something is truly still? At that point, we hit a wall. Not a wall of data, a wall of perspective. Because everything we see is seen from Earth. Our eyes, our telescopes, our instruments, all of them are perched on this spinning rock. And this rock itself is also orbiting the sun. Just like Herschel once suspected, the sun might be moving too. So, how can we figure out what's actually moving? And what's staying still? That's where the idea of a frame of reference comes in. Let's try a simple thought experiment. Imagine you're sitting on a train. You've got a coffee in hand, and a book you're reading. You glance out the window, and see another train stop right beside you. For a moment, it feels like that other train is sliding backward. But hold on. Are you the one moving? Or is it them? Or are you both moving? Here's the thing. Without looking at the ground, you can't really tell. That's the trap of your frame of reference. From inside the train, everything seems still. Your coffee stays in the cup. Your book rests quietly on your lap. But to someone standing on the platform, you're racing by at 80 kilometers an hour. So, who's right? Well, actually both are. Because motion isn't absolute. It's relative. When your only window to the universe is from a moving train, in this case, Earth orbiting a star, and that star is also in motion. Figuring out what's really happening becomes quite the puzzle. And one quiet, patient man set out to solve it. Jacobus. Captain never thought of himself as a revolutionary. He was quiet, cautious. A man who loved numbers more than noise. But the way he worked with those numbers changed our understanding of the universe. Captain was born in mid-19th century Netherlands, by which time Herschel's stellar map was already more than a century old. The idea that we live in a system of stars within what we now call the Milky Way was accepted. But its structure and its motion were still hazy. Telescopes were getting better, but astronomers needed more than just sharper tools. They needed a new approach. And that's what Captain brought. He began gathering data, not just light, not just positions, but proper motions. Over time, how stars slowly drift across the sky. Tiny shifts, often just fractions of an arcsecond per year. But with the right math and enough time, they could tell a story. He collected observations from observatories all over the world. Cape Town, South Africa; Cordoba, Argentina; Sydney, Australia. Piece by piece, he compiled thousands of star catalogs, measuring their brightness, their positions, and their drift. Then, something strange emerged. The stars weren't drifting randomly. They were moving in a pattern, to great cosmic streams, flowing across the sky. At first, the stars seemed to be clumping into two giant rotating groups. But Captain thought harder. What if it wasn't about the stars at all? What if we were the ones moving? How would that change things? Back to the train analogy. Imagine you're walking steadily through a busy square, right in the middle of a crowd. People seem to stream past you from all directions. But maybe you're the one in motion, and everything else only appears to flow because of your frame of reference. So Captain dove into the problem, and he started calculating. And the results? Spot on. It only made sense if the sun itself was moving and carrying us along with it. This motion is called the solar apex. According to Captain's observations, the sun is drifting at about 20 kilometers per second toward a point in the constellation Hercules. It's not a dramatic sprint, more like a steady, silent glide through space. And just like that, the sun lost its status as stationary. But Captain wasn't done yet. He wanted to go further. If we're moving through the starry sky, then what exactly are these stars? What kind of system are we part of? Using the motion and brightness of stars, Captain began to map out what he believed was the true shape of our galaxy. He thought stars were evenly spread through space, and that their brightness faded with distance. Based on this, he came up with a model, a flattened, disc-like structure, about 40,000 light-years across. In this structure, what Captain called the universe, the sun sat near the center. It was our first real attempt to draw a map of the Milky Way. Of course, we now know Captain's universe was far too small. He had no idea about interstellar dust, tiny particles floating between the stars that absorb and scatter light, especially along the plane of the galaxy. This makes distant stars appear dimmer, tricking us into thinking they're closer than they are. As a result, his model underestimated the galaxy's size and shape. But at the time, it was groundbreaking work. Then came the turning point. Astronomers began to take interest in those faint, fuzzy patches in the sky, the so-called spiral nebulae. Some thought they were part of our Milky Way, but others suspected they were something far more dramatic. Entire star systems, in their own right. That's when Edwin Hubble entered the scene. Hubble used the Hooker telescope on Mount Wilson, the most powerful telescope on Earth at the time, to study one of the most prominent of these nebulae, the Andromeda Nebula. In 1923, he discovered something crucial inside it, a type of star known as a Cepheid variable. These stars brighten and dim in a predictable pattern, thanks to the earlier work of Henrietta Swan Leavitt. That pattern could be used to calculate their actual distance. The answer shocked him. Andromeda wasn't just far away. It was way beyond the Milky Way's edge. In fact, it couldn't possibly be part of our galaxy at all. This was a seismic shift. For centuries, we'd believed the Milky Way was the entire universe. Now, it was just one galaxy among countless others. An island in an immense cosmic ocean. But here's the truly important part. By studying these other galaxies, we began to see our own galaxy more clearly. You can't see the Milky Way from the outside. We live inside it. It's like trying to draw the shape of a forest while standing at the roots of a tree. But with Andromeda and other galaxies, we could finally make comparisons. We could observe galaxies from the outside and start asking questions like, does our galaxy also have a spiral structure like that? Does it have a central bulge, a flat disk, or a halo of stars? In the decades that followed, astronomers used this mirror effect, comparing external galaxies to what we observe from inside the Milky Way. They mapped out clouds of gas, star clusters, and different stellar populations. They used radio astronomy to cut through the dust that blocks our view in visible light. Slowly, a whole new picture began to emerge. One key figure was the Dutch astronomer Jan Oort. He carefully studied the movements of stars near our sun. He wasn't just interested in where the stars were. He wanted to know how they were moving. And what he found was strange. If the Milky Way spun like a solid wheel, then every star should move at the same angular speed, like the spokes on a bicycle wheel. But that's not what he saw. Some stars lagged behind, while others moved faster. It looked more like a swirling vortex than a perfect wheel, or rather, like something squeezed into a creaky, uneven shape. These numbers revealed to him that the Milky Way was indeed rotating, but not at a uniform speed. It spun faster near the center, and slower at the edges. He worked out the math behind it, and came up with two constants to describe how stars move in our part of the galaxy. Today, these are known as the Oort constants. For the first time, they gave a real description of the Milky Way's differential rotation. From there, he calculated that our sun is about 30,000 light-years from the galactic center and races through space at over 200 kilometers per second. That's fast enough to circle Earth 7 times in a single minute. At that speed, it takes the sun roughly 225 million years to complete one lap around the galaxy, a galactic year. And the sun, in traveling alone, every star you see in the night sky is making the same journey. Like bees swarming a hive, they all orbit the galactic center. We just don't feel it, because we're all moving together. But if that's the case, what exactly are we orbiting around? To answer that, astronomers needed better eyes, ones that could see beyond visible light. So they turned to radio waves. Specifically, they began mapping the faint natural radio signals from neutral hydrogen atoms. Signals with a wavelength of 21 centimeters, able to pierce through thick clouds of dust that block ordinary light. By tracing this signal, astronomers started charting the spiral arms of the Milky Way from the inside. It was like trying to draw a picture of a forest while standing among the trees, but now they had the right tools. And then came one of the biggest leaps. The Very Long Baseline Array, or VLBA. The VLBA in a single telescope. It's a network of 10 radio antennas, spread out across thousands of kilometers. Imagine placing two telescopes on opposite ends of Earth, one in Hawaii and another in the Virgin Islands. Now imagine sensing them perfectly. Together, they act like a single giant antenna the size of a continent. That's the power of the VLBA. It links 10 observatories scattered across the Western Hemisphere into one super instrument, capable of detecting incredibly tiny motions in the sky. And by tiny, we mean movements measured in micro-arcseconds. That's like spotting a coin on the moon from here on Earth. Astronomers use this system to track cosmic beacons known as masers. They're not visible lasers, but natural radio emissions from clouds of gas around newborn stars. These act like lighthouses in space, bright, compact, and perfect for tracking. Perfect for tracking because they're locked into specific regions of our galaxy. They can help us pinpoint positions and speeds with precision. After years of watching, astronomers have seen these objects slowly drift across the sky. They've measured how their positions change. That's called proper motion. And how their light shifts toward red or blue, which reveals their radial speed, whether they're moving toward us or away. Put all that together, and you get a complete 3D picture of motion. Not just left and right, not just forward and back, but the entire dance of stars across the Milky Way. And that cosmic dance reveals something. It shows stars orbiting the galactic center, but not in perfect circles. Their paths spiral, twisted and stretched by gravity and the galaxy's own structure. Some arms lead ahead, others lag behind. Star clusters sway. Gas clouds get sheared apart under the pull of tidal forces. But there's something else, right at the heart of it all. Something strange lurks there. As those arms and other stars draw closer to the center of the galaxy, something becomes obvious. Their speed skyrockets. Objects near the center are whipping around at staggering speeds. Here's the catch. There isn't enough visible matter there to explain that gravity. There are stars. Yes, there's dust and gas, but nowhere near enough to hold things together. At those speeds, something invisible is anchoring the Milky Way. All that movement, all those calculations, all that precision measuring, it all points to the same spot, near Sagittarius. A dense, intense source of radiation. That spot is called Sagittarius A. It doesn't look like much to the naked eye. Just a faint haze of dust and stars. But in radio wavelengths, it lights up. VLBA observations zoomed in on it and found it's a relatively stationary object. Everything else spins around it. Its mass, over 4 million times the Sun's, yet smaller than Mercury's orbit. In physics, the only thing that fits those numbers, that small, that dense, that massive, is a black hole, a supermassive black hole. It holds the Milky Way together. It sits quietly at the center, barely flickering, while every single star in the galaxy, every planet, every cloud of gas circles around it. But we're not just sitting still. Because stars don't just orbit the center. The entire galaxy is twisting, warping, and swaying. Our little Orion arm rides the waves like a surfer on the ocean, gently bobbing up and down through the galactic plane. But even the Milky Way itself isn't standing still. our entire galaxy is on the move. Drifting, tugged by unseen forces. Picture a car speeding toward you. Engine roaring as it races past. The pitch of the sound rises as it approaches, then drops as it pulls away. That's the Doppler effect. It happens when something that produces waves like sound moves toward or away from you. The waves bunch up as it approaches and stretch out as it moves away. Light does the exact same thing. It bunches up when approaching and stretches out when moving away. When a star or galaxy moves toward us, its light waves get squeezed, shifting slightly toward the blue end of the spectrum. We call this blue shift. If it's moving away from us, the light waves get stretched, shifting toward the red end. That's redshift. Back in the 1910s and 1920s, scientists began using this method to measure the motion of stars and galaxies. One of them was Edwin Hubble, and his discovery was jaw-dropping. He found that most of the galaxies he observed were not standing still. They were moving away from us. And the farther a galaxy was, the faster it was receding. Some galaxies were racing away at hundreds of kilometers per second. Others, at thousands of kilometers per second. Hubble mapped out this relationship, and with each new galaxy observed, the farther the distance, the faster the speed. The universe itself was expanding, and galaxies were just along for the ride. This became one of the greatest discoveries in science. It meant the universe had a beginning. It meant that everything we see today was once much closer together. It even laid the groundwork for the Big Bang Theory. But not every galaxy is moving away from us. One in particular stands out. It's our well-known neighbor, the giant spiral galaxy Andromeda. In 1912, an American astronomer named Vesto Melvin Slipher pointed his telescope at the Andromeda galaxy and measured its spectrum. At that time, scientists were just beginning to understand how redshift and blueshift worked in galaxies. But what Slipher saw completely defied expectations. Like most galaxies, Andromeda did show redshift, but also blueshift, which meant it was heading straight for us. Back then, though, they could only guess the general direction, not the full picture. Fast forward 100 years, technology had advanced enormously. We now have space telescopes, supercomputers, and global networks of radio antennas. Astronomers use data from NASA's Hubble Space Telescope, combined with the Gaia mission, and precision readings from the VLBA. By tracking Andromeda's actual motion over many years, not just the shift in its light, but also its sideways movement, they built a complete 3D trajectory. And their findings confirmed it. The Andromeda galaxy isn't just drifting nearby. It's not going to sling past us. It's locked in. It's on a direct collision course with the Milky Way. And we're heading straight for it too? Andromeda isn't just moving toward us. We're both speeding through the cosmic void. Closing in fast, right now. Andromeda is approaching at about 110 kilometers per second, over 400,000 kilometers per hour, and the Milky Way isn't standing still either. When you factor in the movement of our entire local group, we're closing in on Andromeda at nearly 300 kilometers per second. That means, combined, the gap between us is shrinking at around 500 kilometers per second. But space is huge. Really huge. Andromeda is about 2.5 million light-years away. That's roughly 24 quintillion kilometers, a number so big it hardly feels real. At these speeds, even with both galaxies racing toward each other, at this speed, even if both galaxies are rushing toward each other, the approach is still far too slow to happen anytime soon. So, it won't be tomorrow, and it won't be next year, but about 4 to 5 billion years from now, these two giant galaxies will finally meet. Now, you might picture this as a galactic smash-up. Stars colliding, chaos everywhere, explosions lighting up space. But that's not what actually happens. Galaxies are mostly vast empty space. The stars inside are incredibly far apart. On average, in our own Milky Way, stars are about 4 to 5 light-years apart. That's roughly 40 trillion kilometers. Even in the denser galactic core, they're usually still a light-year apart, or more. To put it in perspective, imagine if a star were the size of a ping-pong ball. The nearest star would be hundreds of kilometers away. So, even if two galaxies crash head-on, most stars will just glide past each other, like ships passing in the night, never touching. However, galaxies aren't completely serene. Some stars might actually collide, especially in those crowded central regions. And a few stars, especially those near the edges, could be completely flung out of their galaxy, adrift in intergalactic space, like cosmic castaways. But the real drama comes from gravity's pull. This invisible force stretches and twists the galaxies, flinging out long tidal tails, ripping streams of stars from their homes, tearing apart spiral arms, and pulling the galactic disks closer and closer, until they finally merge into a single, larger, and more chaotic system. But this full merger doesn't happen in one go. The first encounter is quick, a close pass that triggers the mayhem. But the merging itself is slow. It takes around 1 to 2 billion years to fully settle. It's less of a crash, and more of a slow, graceful dance of gravity. And when the dance ends, something new is born, a giant elliptical galaxy. Astronomers have already named it Milkomeda. It won't look like a spiral anymore. It'll be puffier, rounder, and enormous glowing ball, made of stars, gas, and dust. If our sun is still alive then, it'll likely end up in a brand new orbit. Not where it sits today, not in a neat spiral arm, but in a more elliptical, less stable path, drifting farther from the center. But the Andromeda collision isn't the whole story. It's not the only path our galaxy is on, because the Milky Way, Andromeda, and hundreds of other nearby galaxies aren't just being pulled toward each other. We're also being drawn toward something much bigger and stranger. To know where we're heading, we need to zoom way out. First past our solar system, then past the Milky Way, and even beyond our entire galaxy group. Because galaxies don't just float around alone. They gather into clusters, following gravity like water flowing downhill. So let's start small. Our Milky Way is part of a galaxy group. This group is made up of around 80 galaxies. It's called the local group. It's about 10 million light-years across. The Milky Way and Andromeda are the two largest galaxies in this group. Each is surrounded by smaller satellite galaxies, like the large and small. Magellanic Clouds, or the M32 and M110 galaxies orbiting Andromeda. But this galaxy group is just a tiny part of an even larger galaxy cluster. A galaxy cluster is made up of many galaxy groups, all bound together by gravity. Our local group is just one small member of the Virgo cluster. The Virgo cluster is an even bigger collection, containing over 1,000 galaxies. It's about 65 million light-years away from us. Its gravity is pulling on us. We're not just floating idly nearby. Our entire local group is racing toward the Virgo cluster's center at around 600 kilometers per second. So, within galaxy clusters, you have galaxy groups. But even clusters aren't the final chapter of the story. Clusters themselves come together to form superclusters. These are the largest known structures in the observable universe. They can stretch hundreds of millions of light-years and hold tens of thousands of galaxies. Our galaxy cluster belongs to one called the Laniakea supercluster. In Hawaiian, that name means immense heaven. And it's spot on. Laniakea is vast, truly mind-bogglingly huge. It spans over 500 million light-years and contains about 100,000 galaxy clusters. That includes the Virgo cluster, the Hydrus and Taurus supercluster, the Pavo-Indus supercluster, and the Southern supercluster. They're all interconnected, forming a vast cosmic flow network. So, how do we even know all of this? How do scientists figure out which way galaxies are moving, how fast they're going, and where they might be headed? It all comes down to motion. Over the past few decades, astronomers haven't just mapped where galaxies are. They've tracked how they're moving. To do that, they need more than just redshift and blueshift data. They also need peculiar velocities, a galaxy's true speed, relative to the universe's overall expansion. And that's no easy feat. You can't just snap a picture and instantly know how fast a galaxy is drifting sideways through space. You have to combine several techniques, and one of the most important is the Tully-Fisher relation. Astronomers use this relation to compare the brightness of a spiral galaxy with its rotation speed. If you know how bright a galaxy should be, and compare that to its actual brightness, you can estimate its distance. Once you know a galaxy's redshift and distance, you can figure out whether it's moving faster or slower than the general Hubble expansion. That difference is its peculiar velocity, motion caused by local gravitational influences, not just the universe's expansion. And that's where the real insight comes in. The cosmic flow surveys, Cosmic Flows 2, and later the even more detailed Cosmic Flows 3, combine Tully-Fisher data with surface brightness fluctuations and even supernova measurements to gather motion and distance data for thousands of galaxies. After years of work, scientists built a 3D velocity map of our cosmic neighborhood. It reveals not only where galaxies are in space, but also how they're moving. Galaxies are in motion, and what they found is astonishing. Galaxies aren't just expanding outward like dots on a balloon. They're also streaming in a specific direction, towards something we can't directly see. Something massive. And this flow isn't random. It's coherent, organized. This motion points beyond Centaurus and Norma toward a mysterious patch of space hidden behind the Milky Way's thick dust belt. And that's where the real mystery begins. What exactly is pulling us in? What's pulling us in? Why did astronomers as far back as the 1970s notice this strange kind of flow? Galaxies, including our own, aren't just drifting with the expanding universe. They're moving sideways, on purpose, at hundreds of kilometers per second, all heading in the same direction. But when telescopes try to look that way, they hit a wall. It's what we call the zone of avoidance. It's crammed with stars from our own Milky Way, along with gas and dust, blocking our view of anything behind it. Still, this motion is undeniable. Scientists call the source of this pull the Great Attractor, not because they can see it, but because they can feel its gravity. Whole clusters of galaxies are leaning toward it, and we're caught in the same gravitational stream. Using X-ray telescopes and infrared sky surveys, astronomers pieced together the picture bit by bit. They discovered that behind the plane of our galaxy lies a huge mass concentration. It's not a single object, but a whole region filled with galaxy clusters. The largest of them is the Norma cluster, about 220 million light-years away. And this cluster isn't alone. It's part of an even bigger structure. This region, this attractor, actually sits near the edge of a giant supercluster called the Shapley supercluster. It's one of the largest known superclusters in our corner of the universe. That's what's tugging on us. The Shapley supercluster's gravity is so strong that it bends the paths of galaxies across vast stretches of the cosmos. Even though we can't see it directly, invisible light, its mass, is pulling our entire supercluster toward it at about 600 kilometers per second. Now here's where it gets tricky. This isn't a neat, clear destination. We're not just going to drop into it like a stone falling into a pit. The Great Attractor is part of a cosmic tug-of-war. Gravity doesn't just pull. It warps space itself. So, while the Great Attractor is pulling us in, other forces in the universe are shaping our path too. And one of the strangest influences on that path isn't even a force. It's called the dipole repeller. Let's slow down here. The dipole repeller isn't an object. It's not a galaxy. It's not even something you can see. It's an unusually empty region of space. A cosmic void. There's almost no matter there. No massive galaxy clusters. No real gravity. But emptiness matters. Because, while massive objects pull galaxies toward them, voids do the opposite. They make it easier for galaxies to drift away. Picture this. You're floating down a river. On one side, a waterfall pulls you in. That's the Great Attractor. On the other side, just calm water. No current. No push, that's the dipole repeller. It's not pushing you away. It's just not holding you back. So, the waterfall wins. That's the kind of gravitational current our galaxy is caught in. In 2017, astronomers began to see this more clearly, using Cosmic Flow's 3D data and 3D motion maps of over 18,000 galaxies. What they saw wasn't just a pull in one direction. It was a dipole pattern. Galaxies like ours are on the move, drifting away from the repeller and toward the Great Attractor. But that's not the end of the cosmic journey. If you travel far enough past galaxy clusters, supercluster filaments, and vast cosmic voids, a new pattern starts to emerge. A deeper kind of motion, one that spans the entire observable universe. Every great strand of the cosmic web is in motion. They're all drifting somewhere. Up until now, we've been following Earth's spin and orbit. We've watched the sun drift through the Milky Way, like a leaf in a stream. Then we zoomed out and saw that even the Milky Way itself is on the move. It's part of a massive cosmic flow, headed towards something we can't even see. Imagine standing on a rock that's moving, and that rock is part of a moving system inside a moving galaxy. It's already mind-blowing, but now it's time to go even bigger. It's time to ask the ultimate question. Where is everything in the universe headed? Not just Earth, not just our galaxy, but everything. What is the universe's final destination? To answer that, we have to talk about something strange. Something that doesn't shine or glow. Almost like it's pulling the strings from behind the scenes. When scientists discovered it, it shook physics to its core. And ironically, the story starts with the end of the universe, or at least, with trying to predict how it might end. In the 1990s, two teams of scientists, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were studying exploding stars, known as Type Ia supernovae. These explosions are incredibly bright and happen in almost exactly the same way every time, which makes them perfect mile markers for measuring the cosmos. If you know how bright a supernova should be, and it looks dimmer than expected, that means it's farther away than you thought. The goal was to measure how fast the universe was slowing down. Yep, you heard that right. Back then, everyone assumed that after the Big Bang, the universe's expansion was gradually slowing, with gravity pulling everything back together. But the data told a different story. When they measured those supernovae, something didn't add up. These galaxies weren't just far away. They were way too far. Their light was redshifted more than expected, which meant the galaxies weren't just moving away. They were speeding up. The universe wasn't slowing down. It was accelerating. Now picture this. You're a physicist, and suddenly you realize that every prediction about the universe's future is wrong. That's exactly what happened in 1998. But instead of ignoring it, both teams double-checked everything. And still, they kept getting the same result. Something invisible, something powerful, was tearing the universe apart faster and faster. They called it dark energy. We don't know what dark energy is made of. We don't even know if it's a thing at all. But we do know it's real and it rules the universe. In fact, out of all the energy and matter that exists, about 70% is dark energy. To grasp how bizarre that is, think about everything you've ever seen, touched, tasted, or heard in your life. Every star, every planet, every atom, all of it makes up less than 5% of the universe. Another 25% is dark matter, an invisible glue that uses gravity to hold galaxies together. What's left is basically the biggest piece of the universe. It's the silent force that's tearing the universe apart. So, what could it be? Here's where things get tricky. Physicists have a few guesses. The simplest idea is that dark energy is just the vacuum energy of space. Even though space looks empty, it's actually not. It's filled with quantum fluctuations, Tiny bursts of energy that flicker in and out of existence, appearing and disappearing. Now here's the fun part. When you run the math, quantum theory actually predicts that even empty space should have energy. But that's not the craziest bit. The crazy part is how much. It predicts that vacuum energy should be stronger than what we actually observe, by a factor of 10 to the power of 120. In other words, quantum theory's estimate of the real value overshoots by a staggering margin. This is the single biggest mismatch between theory and observation in the history of physics. It's like trying to weigh a feather, and your calculator says it's heavier than the entire Earth. Yeah, something's way off. And that's the problem. This so-called vacuum energy, the energy of empty space, doesn't just sit there quietly. According to Einstein's equations, energy and pressure shape the fabric of space-time. Which means, if space really does have energy, it will affect how the universe expands. And this is where dark energy comes in. We've observed that the universe is expanding faster and faster. So, whatever's causing this acceleration must be built right into the fabric of space itself. That's why scientists think vacuum energy might be what's driving the expansion. Maybe dark energy is just the energy of empty space. But if that's true, then quantum theory's predictions should match what we actually see. But they absolutely don't. It's not just a little off. It's catastrophically wrong. So either our theory is flawed, or we're missing a massive piece of the puzzle. Now let's try to picture it. Imagine space as a giant loaf of raisin bread. Yes, bread. Galaxies are like raisins baked into the dough. As the bread bakes, it rises, and the raisins move farther apart. That's the universe expanding. But now imagine that halfway through baking, something cranks up the heat. The dough doesn't just rise. It starts expanding faster and faster. That extra pushes dark energy. The bigger the bread gets, the faster it grows. Because dark energy isn't something sprinkled into space. It is space. The more space there is, the more dark energy there is. It doesn't dilute. It doesn't run out. And that's what makes it so scary. Here we are, watching the universe expand faster and faster, driven by this runaway engine we call dark energy. This invisible, untouchable force doesn't clump, doesn't slow down, and the bigger space gets, the stronger it becomes. That's already weird enough. But here's the truly unsettling part. Where is this taking us? If dark energy keeps doing what it's doing, pushing, stretching space even more, so what happens in the long run? That brings us to the entire universe and one of the most chilling predictions in all of cosmology. It's called the Big Rip. Here's how it works. Right now, in our universe, gravity is still strong enough ... to hold things together. Galaxies aren't being torn apart. Stars still orbit around their galactic centers. Planets cling tightly to their stars. Even though space is expanding ... the forces inside galaxies are stronger than the pull of expansion between them. But dark energy doesn't play by those rules. It keeps growing, relentlessly. In some models, it doesn't just speed up the universe's expansion ... It speeds up the speed up. Imagine you're in a car going downhill ... and you keep going faster and faster ... while the slope keeps getting steeper. That's the Big Rip scenario. At first, you wouldn't notice anything. Galaxy clusters would slowly drift apart. the Milky Way, and the Andromeda galaxy would no longer be on a collision course. The space between them would grow too fast. But it wouldn't stop there. Even galaxies themselves would start stretching, not just pulled apart, but torn from the inside out. Gravity would weaken. The bonds holding stars in place would break. Then, star systems like our own solar system would come apart. Planets would drift out of orbit. Moons would vanish into the void. The tidal forces keeping everything balanced would be gone. And it wouldn't stop. As the acceleration increases, even Earth itself wouldn't be safe. The expansion force would grow so strong, it would overwhelm the electromagnetic forces that bind molecules together. The crust would shatter. Atoms would split apart. As space itself stretches beyond what any particle can survive. Even the building blocks of matter could be torn apart. In the final moments before the Big Rip, the universe would be a storm of scattered fragments. 22 billion years from now, there would be no more galaxies, no stars, no atoms, only pure, unbound energy, flickering in a sea of nothingness. That timeline is just one model's guess. It could happen much sooner, or never at all, because it all depends on how dark energy behaves. And we still don't fully understand it. But not every theory ends in destruction. Some go in the complete opposite direction. Here's another idea. It starts with a question. What if the universe's expansion doesn't go on forever? What if, at some point, gravity fights back? You see, in the early universe, everything was hot, dense, and expanding But gravity was pulling inward, trying to slow it all down. That tug-of-war has been going on since the beginning. For a long time, scientists thought gravity might eventually win. This is the Big Crunch theory. In this version of the story, expansion is only temporary. One day, dark energy might weaken. Or, maybe it was never permanent to begin with. If that happens, gravity could take control again. At first, it would slowly start pulling everything back together. Galaxies that once drifted apart would move closer again. The structures would reverse. The great cosmic web would shrink. Billions of years later, the universe would be contracting, with everything being squeezed into a smaller and smaller volume. The temperature would rise. The night sky would grow brighter. It's not because new stars are being born, but because in a universe that's shrinking, old stars crash into each other. Space-time itself would curl inward like a clenched fist. In the final seconds, the entire universe would become a single, blazing hot, dense point. And then, it might simply end. Or it could start all over again. The Big Crunch has a kind of poetic symmetry. The idea that the universe ends where it began. The Big Bang would just be one act, in an endless cycle of expansion and collapse, happening over and over forever. But there's a problem with that picture. The math doesn't quite add up. So far, everything we've observed, the redshift of galaxies, the cosmic microwave background tells us the universe isn't slowing down. It's actually speeding up, which means gravity ain't winning the battle. At least not yet. So, unless there's some huge change in dark energy down the road, the Big Crunch just doesn't seem likely. But here's the thing. We still don't fully understand what dark energy actually is. It's basically a placeholder term for something we can measure, but can't yet explain. We know it's making the universe expand faster and faster. We just don't know why. If someone could uncover the true nature of dark energy, it wouldn't just be a breakthrough. It would be Nobel Prize material. Until then, we can only see what lies ahead of us. Still, there's another possibility, another future. That's not as violent as a tear or a crush. No explosions, no collapse. It just keeps going. And maybe that's the most haunting ending of all. It's called the Big Freeze, a universe that doesn't die in violence, but in silence. Here's how it goes. We've talked about dark energy, how it pushes the universe to expand faster and faster. And we've said that unless something major changes, this expansion will just keep going. Now picture this. The universe stays on that path. Galaxies drift farther and farther apart, never slowing down. The stars inside them grow old, burning through their fuel one by one. It's a chilling thought, an endless fade out. And it's not just speculation. It's backed by some of the best data we have. Andrei Lind, a Russian-American physicist, is famous for his work on inflation theory. He's contributed models that support this ending. Based on measurements from tools like the Planck satellite and massive sky surveys, the expansion rate matches the cosmological constant. That means dark energy could remain unchanged over time. Not growing, not shrinking, just humming along, gently stretching space. If that's true, then the Big Freeze isn't just a possibility. It's the most likely fate of our universe. So let's zoom out now and trace the future, step by step. Right now, in our current era, galaxies are still relatively close. Places like the Orion Nebula are still giving birth to stars. Planets orbit their suns. Life breathes. Black holes devour matter. The cosmos still glows with energy. But fast forward far into the future. Say, 100 billion years from now, black holes are devouring the universe. Yet the cosmic web still glows with energy. But countless ages have already passed. Fast forward 100 billion years. By then, the observable universe we can see will have shrunk dramatically, not because the universe itself is getting smaller, but because the space between us and faraway galaxies is expanding faster than light can travel. Those galaxies will slip beyond our cosmic horizon. We'll never see them again. They'll still exist, but forever out of reach, like ships sailing beyond the edge of an endless sea. Given enough time, even the nearest galaxies will fade from view. Eventually, the Milky Way and the Andromeda galaxy will have long since merged into one giant elliptical galaxy. A lonely island, floating in a vast, dark, silent ocean. But the life of stars can't last forever. Stars are born from clouds of gas, mostly hydrogen. And that fuel won't last forever. When stars go supernova or shed their outer layers, they recycle material back into their galaxies. But over time, this recycling slows down. The fuel runs out. It's estimated that about 1 trillion years from now, all star formation in the universe will stop completely. The remaining stars will slowly burn through the last of their fuel. Red dwarfs, the small, cool, and dim stars, can survive for trillions of years. They will be the last faint glimmers in a pitch-black sky. But even they will eventually burn out. All that will remain are remnants. White dwarfs, neutron stars, and black holes. This is when the so-called degenerate era begins. An age with no new stars, no starlight. The universe will be filled with cold, collapsed objects. stellar corpses and black holes. Still hungry. They'll devour whatever remains. Time keeps ticking on. Over the next 10 to the power of 40 years. That's a 1. Followed by 40 zeros. These stellar remnants will decay. White dwarfs will cool until they become black dwarfs. Neutron stars may remain stable for eons. But black holes have their own ticking clock. According to Stephen Hawking, black holes aren't eternal. Through a quantum effect called Hawking radiation, they slowly evaporate. Over time, they lose mass. Painfully slowly. A black hole with the mass of our Sun would take roughly 10 to the power of 67 years to vanish completely. Just think about that number. Our entire universe, right now, the universe is about 13.8 billion years old, compared to the timescales we're talking about. That's nothing. In the era of the Big Freeze, time stretches on, far beyond anything we can truly imagine. Eventually, every black hole will evaporate, vanishing one by one. In a faint flash of radiation. No more stars. No more stars. No more light. The universe becomes a sea of particles. Electrons and positrons. Maybe a few decaying protons. Drifting alone through an ever-expanding, frigid cosmos. Temperatures drop to absolute zero. Not because there's no heat left, but because there's nothing left to generate it. No fusion. No gravity pulling matter together. Just particles scattered through an ever-growing void. Even protons themselves might not survive. If proton decay turns out to be real, then all matter could simply dissolve away. Some models predict this could happen within 10 to the power of 36 years. And then what's left? Nothing. Just a faint trace of radiation. The afterglow of a universe that was once full of stars, galaxies, and life. The universe keeps expanding until everything is too far apart to ever interact. Too cold for anything to change. Even the concept of place itself loses all meaning. The laws that gave birth to everything still exist, etched into the cold, indifferent void. But now, there's no one left to read them. And that will be the universe's final fate.